Hello everyone, my name is Gabriel Beltran from Instituto Tecnológico de Aragón, ITA, and the name of my presentation is Development of a Digital Engineering Tool for Estimating the Impact of Microdefects on the Mechanical Response of 3D Printed Filaments. This work has been developed within the European project eClimabuild and in collaboration with the companies IRES from Belgium and BioG3D from Greece. This slide shows the index of the presentation, so let's move on the introduction. On these graphs, it could be observed that the construction industry accounts for 35% of energy consumption and the 38% of CO2 emissions in the European Union. Then, one of the main objectives for the year 2030 is to greatly reduce gas emissions, as well as to increase the use of renewable energies and energy efficiency in this industry. Therefore, an urgent need is present for a deep market transformation by deploying efficient materials and technologies and the real implementation of nearly zero energy buildings. This is the context of the European eClimabuild project, in which 27 partners are involved and whose main objective is to create an open access ecosystem for developing, upscaling, and testing innovation in building envelope materials and technical systems via its 9 pilot lines to reach nearly zero energy buildings balance. At the same time, eClimabuild will aid some high-tech companies in expanding and managing the increasing complexity of technology, facilitating the conversion of research outcomes into innovations. In this project, my institution, ITA, leads the analysis of buildings' elements performance by means of multi-physics virtual prototypes and digital twins. As I have mentioned, one of the main objectives of this project is the development of zero-energy building. This type of buildings present a net zero energy consumption, which means that the total amount of energy used by the building on an annual basis is equal to the amount of renewable energy created on the site. To achieve a building with net energy equal to zero, there are solutions based on design and passive strategies. Among these strategies is 3D printing customizable components for indoor environmental quality improvement. In this case, the 3D printing process is fused filament fabrication, where the material is melted and deposited layer by layer to create a three-dimensional object. However, during this process, defects could appear. To detect these errors, some manufacturers opt for an online monitoring of the production processes by capturing images. As a result, rich information is captured through these images since the defects are categorized and dimensionally characterized by means of machine learning techniques. In this case, two main types of defects have been identified, underfilling and overfilling, and their impact on the mechanical response of the printed filaments will be estimated. This system for capturing and categorizing 3D printing defects through image capture was developed by two of the eClimabuild project partners, IRES from Belgium and BioG3D from Greece. The main objective is to analyze the influence of the microdefects on the mechanical response of the 3D printed filaments. To fulfill this objective, we propose the following methodology, which consists of two steps. The first one is to generate finite element mechanical models, where the geometrical dimensions of the defects have been parameterized to relate them to the stiffness variation that occurs in the filaments. And the second one is to build a metamodel from the simulation results, which allows to obtain the variation of the stiffness in real time. These metamodels are implemented in a user-friendly visualization virtual tool. In the following section, Material and Methods, the strategy carried out is described in detail. The first step of this strategy consists of defining the parametric CAD models. As it could be observed on this scheme, two parametric models have been developed, one for each defect, underfilling and overfilling. This model consists of only 3 filaments in order to study the micromechanical response. The parameters considered in these models are characteristic dimensions which describes both the geometry of the filaments and the defects. These parameters are described in the following section. For underfilling and overfilling cases, the first parameter considered is the filament length, parameter L, which corresponds to the defect length captured on the picture. The second one is the filament height, parameter A, which is highlighted on the pictures. And the third one is the defect width, parameter C, that in the case of the underfilling is lower than the nominal width of the filament, and in the case of the overfilling, this is higher than the nominal width of the filament. Finally, it should be noted that the nominal width of filament is constant for all cases, with a value of 0.57 mm. Additionally, in order to reproduce the geometry of the defects observed, an initial zone and a transition zone of the defects have been defined on both ends of the filaments. Once the three geometrical parameters to be considered have been defined, a design of experiments is generated. To carry out the parametric analysis, a design of experiments has been defined for each defect. This design allows to play the key simulation and is defined for covering a wide range of common situations in terms of geometry of the filaments and the defects. The range selected for each geometrical parameter has been decided based on the pictures and information captured. A full factorial of extreme values and a random lighting hyperview technique has been used for defining the design of experiments, with a total number of 1024 simulations for each defect. Once the batch of simulations have been defined by means of the design of experiments, the finite element models developed are described in the following section. For each case defined on the design of experiments, a finite element model has been generated for reproducing the mechanical response of the filaments by means of the simulation of a tensile test. The material used in the simulation for PLA is a linear elastic model with a Young's modulus of 3,384 megapascals and a Poisson's ratio of 0.38. The boundary conditions applied in the simulation are displayed on these figures. At one end of the filaments, an axial strain of 0.05 is applied. By applying this deformation level, it is ensured that the material responds in the linear elastic regime. The other end of the filaments remains fixed during the simulation. As a result, the axial reaction force is obtained for each case. From these simulation results, both the stress and the equivalent Young's modulus are obtained for all cases by means of the following expressions. It should be noted that the reference equivalent Young's modulus has been calculated from a finite element simulation result for a case without defects. Once the reference equivalent Young's modulus has been obtained, the stiffness variation is calculated for each case with the following equation. For each defect, a table, as is shown in the image, has been generated. In this table, the value of the three geometric input parameters, filament height, parameter A, defect width, parameter C, and filament length, parameter L, are related with the corresponding stiffness variation for the 1024 cases simulated. Additionally, a study of the results obtained in the simulation has been performed. As it could be observed, there is a very clear correlation between the parameter C, defect width, and the stiffness variation. This is due to the lower the width, the lower the cross-sectional area of resistance, and therefore the greater the loss of stiffness. However, for the height and length of the filament, parameter A and parameter L, no clear correlation with the stiffness variation is observed. For the overfilling defect, a similar trend of the results is observed. As it has been already described for the case of underfilling, a higher value of parameter C implies a higher resistance section and therefore a higher stiffness variation. For the length of the filament, parameter L, a slight correlation is observed with the stiffness variation, while no correlation is observed for the height of the filament. And finally, let's move to the last stage of the methodology, which is based on the generation of the metamodels and the virtual tools. The results obtained in the simulation are used to feed the generation of the metamodels. Finally, a virtual tool is built from these metamodels. these metamodels have been generated by means of Python package developed by ITA. This Python package includes an analysis tool dedicated to virtual development of systems and moreover allows the realization of metamodels by means of machine learning techniques. Metamodels could be saved as an external file, .metadata, which can be implemented later in secondary applications. For this case, two metamodels have been generated, one for each defect studied. These metamodels are used to generate response surfaces, which allow to know in real time the value of the stiffness variation for a given values of the geometrical input parameter. As I have mentioned on the previous slide, the PyMetaModels Python package allows the analysis of the data used. Then, a sensitivity analysis has been performed in order to correlate each input parameter with the output parameter. For both cases, it is observed that the parameter C, defect width, is clearly the one that most affects the output variable. This is consistent with the analysis of the simulation results shown previously. By means of this Python package, the accuracy of the response surfaces obtained could be also evaluated, comparing the real values which have been used for fitting the metamodel and the results predicted by the metamodel. As it could be observed, the prediction of the metamodel is very high, with a coefficient of determination of 1 for the case of the underfilling and 0.99 in the case of the overfilling. Finally, the response surface of the metamodels generated with this Python package are depicted on this slide. These 3D graphs show that for the underfilling defect, the reduction of the stiffness is notably high, reaching a reduction of 50% for some studied cases. For the overfilling defect, the stiffness increased up to 12% in some cases. The metamodels obtained are integrated into a virtual engineering tool. Then, two virtual tools have been developed, one for each defect. This digital engineering tool consists of a simple and easy-to-use visualization platform with user-friendly visualization techniques. In this slide, an example of how the virtual tool works for the underfilling defect is shown. As it could be observed, the user can easily vary the value of any of the three input parameters, obtaining in real time the output value, which in this case is the stiffness variations. Then, this tool allows to exploit the results generated from finite element simulations. The main conclusions drawn from this work are summarized in the following section. In first place, parametric geometrical finite element models for the two defect types have been developed for studying their influence on the mechanical response. The simulation results allows to conclude that the defect width, parameter C, has the greatest influence on the stiffness variation. In the case of the underfilling, a stiffness variation up to 55.4% is obtained, while in the case of the overfilling, the stiffness variation reaches values up to 13.2%. In second place, two metamodels, one for each defect, have been developed based on the simulation results. These metamodels have been generated with Python package developed by ITA. Finally, these metamodels have been integrated on virtual tool, which allows the user to obtain in a simple way and in real time an accurate estimation of the variation of stiffness as a function of the geometric input parameter. For concluding this presentation, in this section we define possible lines of future work arising from this study. Due to these metamodels can be exported in a Python file, we propose as possible line of future work to integrate them into production line processes, allowing to predict the mechanical response of the filaments from the information and images captured during the printing process and to take real-time decisions on the parameter of the production process. Finally, we consider that the methodology developed is a powerful channel to provide an end-user-focused virtual environment to exploit the previous knowledge. Therefore, it could be applied in multiple fields of science and technology. I have now come to the end of my presentation, so thank you very much for your attention.